In this video, we're going to be talking about aromatic compounds. We're going to start by looking at benzene itself, talking about structure, stability, and bonding, and then we're going to look at compounds related to benzene, and we're going to take a look at spectroscopy. Later this chapter, we're going to look more broadly at what it means to be aromatic, and we'll see other examples of types of aromatic compounds. The compound benzene was known in the early 1800s. Scientists knew that it was unsaturated with a molecular formula of C6H6. It was known that all hydrogens were equivalent. So with all this unsaturation, it could be an alkene, it could be an alkyne. There are actually many structures that had been proposed. But another important piece of information is that benzene did not undergo reactions that were typical of alkenes or alkynes. In 1866, Kekule proposed a ring structure, and this has the alternating double bond, single bond all the way around the six-membered ring. And so this has the formula C6H6. This is the currently accepted structure of benzene, except that we also have to keep in mind resonance. So in our first representation, this is drawn as if we have double bond, single bond, double single, double single. But we can draw another resonance structure, and so this arrow represents the imaginary movement of electrons. So we can imagine that these electrons move here, and so that gives us the double bond here, here, and here. Now, in terms of resonance, we understand that neither of these structures exists. What actually exists is the resonance hybrid. So we don't have double bond, single bond. Instead, our electrons, our pi electrons, are delocalized throughout the ring, giving us instead more of a 1.5 bond all the way around the ring. This representation is called the Robinson symbol, and this gives us a convenient shorthand for a benzene ring, but the circle should also serve as a reminder of resonance. So often we will draw benzene with a Kekule structure, but sometimes we will draw benzene using the Robinson symbol, but we always want to think about benzene as the resonance hybrid. Now, what is it that's special about benzene? So we talked about resonance, and keep in mind resonance is the delocalization of electrons, and by spreading out or delocalizing electrons, that leads to stability. So how stable is benzene? Let's consider the heat of hydrogenation as a way to compare the stability of different molecules. Well, here we have an energy diagram for the hydrogenation of cyclohexene to give cyclohexane. And the heat of hydrogenation, so the energy that's given off, is 120 kilojoules per mole. Now, if benzene was just a regular triene, nothing special, we just happen to have 3 alkenes instead of 1, we would expect that the heat of hydrogenation would be 3 times 120, or 360 kilojoules per mole. But what was found experimentally is that the heat of hydrogenation was only 208 kilojoules per mole, which means the energy of benzene is not way up here. Instead, it is much lower than would be expected. How much lower? Well, we have a difference of 152 kilojoules per mole of what's called resonance energy. So that extra stability compared to the hypothetical cyclohexatriene. And so this gives us information on how much stabilizing is brought about because of the delocalized electrons. Let's focus on the structure and bonding in benzene. So we can draw the Kekule structures to look like this, but keep in mind all of these carbons are sp2 hybridized. Now looking at other types of compounds, if you have a single bond between 2 sp2 hybridized carbons, that has a bond length of 146 picometers. If we have a double bond between sp2 hybridized carbons, that has a typical bond length of 134 picometers. Experimentally determined carbon-carbon bond length in benzene is 140 picometers. So it's not a single bond or a double bond. We can think of it as a 1.5 bond. Now think about the hybridization and what that means. Because each carbon is sp2 hybridized, if we look at this carbon, for example, there is an sp2 orbital coming forward that overlaps with this carbon. There is an sp2 hybridized orbital that goes back that overlaps with this carbon. And there is an sp2 orbital that comes out this way that would overlap with a hydrogen. But in addition to the 3 sp2 orbitals, we also have a p orbital. So focusing on the individual carbon, we can look at this part. But if we think about it all together, focusing on the p orbitals, so what we have then is all p orbitals are overlapping in a continuous pi system. Now we have the p orbitals above the ring, and we have interaction among the p orbitals below the ring. And of course, I drew that the exact opposite of how we have this picture here. But what we get is kind of a sandwich where we have this top part with all of our electron density above the ring, and then our bottom part with all of the electron density below the ring. So we can think about this delocalization of electrons throughout this continuous pi system as a way to try to understand the special stability of benzene. Rather than a vague concept of p orbitals overlapping in a continuous pi system, we could instead apply molecular orbital theory to try to explain benzene. Now you can consider some simple examples of molecular orbital theory, such as 2 hydrogen atoms coming together to form a hydrogen molecule. And in some cases, it's relatively straightforward to draw your molecular orbitals based on the linear combination of atomic orbitals. Now, if we're looking at benzene, if we have, so here's our 6-membered ring, which I'm trying to draw kind of on its side. If we have all of our p orbitals, the red phase on top, and the blue phase on the bottom, then that gives us this as our molecular orbital. But it's not really obvious how to draw all of these different molecular orbitals, but that's not something that I'm going to ask you to do. So instead, just look at the results of the molecular orbitals. We have a pi molecular orbital, pi 1, pi 2, and pi 3. These are all bonding orbitals. And then we also have antibonding orbitals. Because we have 6 pi electrons, we fill up our 3 lowest molecular orbitals, which are all bonding orbitals. Now these are all low energy, and so it is more stable than the atomic orbitals, which is why benzene has special stability as a molecule. Now, in addition to benzene itself, we have a number of compounds that are related to benzene. Some of these we're looking at benzene with a substituent. And in other cases, we're looking at a benzene molecule fused to another benzene molecule. So with benzene and related aromatic compounds, this is where the IUPAC naming is kind of thrown out the window. There are so many common names that are really, truly common. So I want you to be familiar with these. Okay, so starting out, we have benzene itself. The next compound where we have a methyl group replacing one of the hydrogens of benzene, this is called toluene. Where we have an OH replacing one of the hydrogens of benzene, this is called phenol. If we have an amine group, this is aniline. Where we have an aldehyde, this is called benzaldehyde. And then the carboxylic acid, this is called benzoic acid. So that's this compound here. So be familiar with these common names because this is what you're going to see, this is what we're going to use. Now for other compounds, we can focus on benzene as our base name and then just look at substituents or branches on the benzene. So this one, for example, could just be called bromobenzene. And this one, this is our tert-butyl group or T-butyl. So this can just be called T-butyl benzene. Alternatively, this could be named as an alkyl halide. And in that case, the benzene group as a substituent, remember this is a phenyl group. And so this compound would be phenyl bromide. Please notice a difference. Phenyl with a YL, this is benzene as a substituent. Phenol with the OL, this is benzene with an OH. So this is the alcohol. Let the OL remind you that it is an alcohol. Now let's look at a few more examples of naming. What if we have multiple substituents, multiple branches on the ring? Well, this could be 1, 2. We can just call this 1, 2 dash dibromobenzene. And then the next one would be 1, 3 and 1, 4 dibromobenzene. But there's another naming system where if we have our two substituents that are on adjacent carbons, this is called ortho. When the groups are 1, 3, this is meta. And when the groups are across from each other, this is called para. We say it ortho, meta, para, but we would write it, so let's just look at the last one. This one would be para dibromobenzene. So we don't have to give the numbers 1, 4. By saying that it's para, that tells us that the substituents are 1, 4. Sorry, I don't have enough space. Let's look at a few more examples and notice for this compound we have benzene with a methyl branch and a bromine branch. But benzene with a methyl has the common name toluene. So rather than naming this as a disubstituted benzene, we instead name it as a substituted toluene. So this can be called orthobromotoluene. So the toluene, this carbon is automatically number 1, and so this carbon then would be number 2. So orthobromotoluene or 2-bromotoluene. The next one would also be named as a toluene, and it gets a little bit cumbersome to call this ortho meta, so that's not used, and instead we would just use the numbers. So once again, because we're naming this as toluene, this is automatically carbon 1, 2, 3. So this would be 2, 3 dibromotoluene. And then one more example that is named as a toluene. If this is 1, we can go clockwise or counterclockwise, it doesn't matter. 2, 4, 6. So this is 2, 4, 6 trinitrotoluene, better known as TNT. In addition to benzene-related compounds that have a substituent on the benzene, we also have compounds that are multiple benzene rings. And here we have an example of 2 rings together. This is naphthalene. This is in mothballs. We have anthracene and phenanthrene. Both have 3 benzene rings, but these are fused in a linear way, whereas here the rings are fused in an angular way. There are common names for these compounds, and then there are rules for how to number them and how to name substituted versions of them. We're not responsible for that. You can use the book as a resource if you need to.